It's our last meeting together. It's been a fun summer. It went by like that. And part of why it went so quick for me personally is when I found out how good Labster is, every week I had to create 2 new labs, which is not an easy trick, but I pulled it off. But more importantly, you pulled it off with a limited amount of time, because normally in the summer, if you were at COD in a classroom, we'd have 8 hours lecture plus lab per week. I only was allowed to do what, 5 hours, and still with that, you guys pulled it off. Thank you, thank you, and thank you. And one last time, I better do it. It's time to get started. All right, couple things. First of all, I've sent out the password email that you should have received, or look in your student email for the final exam. It's due tomorrow, 9 a.m. Take as much time as you want. You should have already, if you haven't, downloaded it from the assignment area. There's a periodic table, same one you've had all semester, and instructions how to upload it in case you haven't figured it out. Luckily, all of you have figured it out, because in test 4, everybody was able to get it uploaded as a PDF file. In the email sent with the password, I mentioned there was one very minor mistake I made on the final, and that is problem 43. I have as 2 points each. It really is 1 point. Now, one thing I will say is that by Sunday, 1 p.m., hopefully sooner, I will have in Blackboard your final exam score, all your points. I already last night or yesterday afternoon uploaded all the lab and your lab total in Blackboard. That should be there. Check and see if it's correct. If not, email me. I'll still change things. And I will have all that, including your letter grade in Blackboard. In COD My Access, I think that's what it's called. Each school I teach at has similar names. I also will be uploading your course grade. Sometimes that takes up to 24 to 36 hours before you can see it. But you can see it immediately once I post it in Blackboard, and it'll be the same grade. I will not be sending out emails with your point total for each question. Why? Because I'm lazy. And also during the semester, if you were at COD, I give the final and I never return that. I do keep it, and I keep the scores in case anybody disputes it. I will tell you this. If you're within 10 points of a cutoff for a grade, I will go back and totally regrade your final. And with a hand calculator, oh, it disappeared. I can't find it. With my trusty hand calculator, and also with a spreadsheet, I'll recalculate your score to make sure I didn't make a mistake. That's if you're within 10 points of a cutoff. Because as far as I can remember, I have a good memory. I don't know if I told you I have a photographic memory for a lot of things. I have yet to make a mistake on a test more than 5 points for a final. Never. But still, there might be a first time. That's why it's rare to make it. And that's why if you're within 10 points of a cutoff, I will. As per my syllabus, I cannot discuss grades via email or phone, but because of the virus, I will be able to discuss grades if you're ever interested via Zoom. I can always set up a Zoom meeting. After today, we're done, but it's been a pleasure. My only regret this semester was that if we were in COD in the main campus, taking it during the lab, I'd have the whole semester, I walk around, I get to talk to students, I get to meet you. This way, a lot of you are just names on the screen, which I thought about it last night. Next semester, I will be asking students to, in small groups, meet me with a camera on if they can, so I can talk to them, just get to know you more than a name on a screen or on a test. Some of you got to know, and thank you. All right, let's go through some important information. Last day I'll be doing this thumbs up. You people, you see the whiteboard. Thank you. Don't forget to write on your thumb, I was a Dr. White's thumbs up person. Nah, you just get a tattoo. All right. One of the things that I didn't have on test 4, but I will have on the final, is dealing with radiation. And one of the things you should know, fusion, that's two small atoms combining to form excuse me. And yes, I did cover my nose with my elbow. All right, in fusion, two types of reactions, nuclear reactions, you should know. First one, fusion. That's when you have two small atoms combining together to form a larger atom. And when this happens, you give off a lot of energy. And you should know an example in our daily life. Where do you see a fusion reaction? And the answer is the sun. Now, how do I remember that? U in fusion, U in sun. Simple, but effective. All right, the other one is fission. I think I'm spelling it right. If not, you spell it right. And this is larger atom and this is in fission. You have a smaller atom, a larger atom decomposing to a larger atom plus energy. An example of fission is our nuclear reactors that make electricity. And they give off energy, which heats water, which makes steam, which drives a turbine, which turns to make electricity. Just like the turbines and dams on the West Coast that make electricity. Now, again, you should know the difference between fusion and fission, and you should know an example of each. And the way I remember is fusion, sun, and the other one, fission, nuclear reactor, or think a reactor. All right, now another important aspect of nuclear energy and radiation is the concept called the half-life. By the way, I never told you this, but red is my favorite color. Just look at my ring the next time you see it on the screen. That's not my birthstone. That's my favorite color stone. All right, half-life, abbreviated by T1 half. That's the amount of time, in that amount of time, whatever radioactive material, at the end of that, you have half the material. So again, the half-life, which you should know, T1 half-life, that's the amount of time for half the radioactive material to decompose into non-radioactive material. Let's take a look at something. Hang in there, I'll be finished soon. All right, let's take a look at this. If you have 32 grams of studonium, new material I just invented, with a half-life of 3 years, how much studonium will you have after 6 years? So I'm going to let you try this one out yourself, and then I'll do it. So go do it. I'm being real mean this morning. My last day, why not? I should rephrase that, my last class this summer. Oh, by the way, Shahana, did you get my email? That's one of the things I always try and do is respond to any student's email quickly. Even though I have 4 email accounts and I get about 100 emails a day, most of them I just delete from the title. So once in a while, a student's email will slip through the crack, but that's rare. All right, time's up. Let's do this. Now, there's a simple way to do this. First of all, what's the half-life? 3 years. What do you start with? 32 grams. For each 3 years, this will cut in half. So half of that, if I'm doing my math correctly, is 16 grams. But you've been asked for 6 years, so this is 3 years. We'll do another 3 years. Half-life, this is cut in half, and the answer is 8 grams. On this type of problem, I don't enforce significant figures. And that would be your answer. How much would be left after would be the answer 8. So that's what you should know for radiation. The rest of it, you don't have to know. All right, can everybody see test 4 review rate of reaction? Oh no. Can you see it now? I got a couple people doing this. Let's do a second check. Everybody see it? Thumbs up, people. Thank you. I'm going to miss you. All right. Let's go back. Collision theory. Remember, there are 3 things you should know. Molecules must collide. The colliding molecules must have a minimum amount of energy, the activation energy, and colliding molecules must have the proper orientation. For rate of reaction, important factors that influence it. One is the physical nature of the reactants. The other is the reactant's concentration. And one of the most important is temperature. And there's a rule of thumb that you should know, which I asked on test number 4, is the rate of a chemical reaction doubles for the every 10 degrees increase in reaction temperature. Now, another thing that will affect rate of reaction is catalyst. You should know how to draw an energy diagram for exothermic and endothermic reaction. I went through one on Monday, so I'm not going to do it today. Dr. White's lazy on the last day. Chemical equilibrium. What do you know? At equilibrium, the forward and reverse rate of reaction are the same. At equilibrium, the forward and reverse rate of reaction are the same. And you see that by this double-headed arrow. And A reacts with B to make C and D. The coefficients are important, W, X, Y, Z, because you should know how to write the equilibrium constant. It's the concentration of the reactants. I got that backwards. Of the products divided by concentration of the reactants. And how do we show that? By putting in a bracket, that means moles per liter, or whatever's in a bracket, to the power of the coefficient. Remember, this is a multiplication, not an addition. That's a common mistake students sometimes make. So here, each concentration of a product to the power of the coefficient of the product divided by the concentration of each reactant to the power of the reactant. Now, magnitude, how large, K equivalent, the equilibrium constant, conveys information how far the completeness of the reaction has occurred. And the larger K equivalent, when, I'll write it, when K equivalent is much greater than 1, in a crude description, there's always going to be more products than reactants. And this means concentration. All right. If K equilibrium is much less than 1, then the reactants concentration are greater than the products. Next, we moved on to Le Chatelain's principle. An equilibrium shifts to the side to reduce the stress put on the equilibrium. And different things that will affect stress are concentration, how much of a reactant or product is present, do you increase or decrease it, and temperature, exothermic, endothermic. Remember, when you put a reaction in boiling water, what you're really doing is adding heat. When you put it in an ice bath, you're removing heat, and that's very important. And if we look at chapter 15, practice problems, and once again, I'll call them those fantastic thumbs up people. Do you see practice problems on the screen? Thank you. Oh, by the way, I mentioned energy diagram. Here's an example, exothermic. That means your product have less heat than your reactants because you lose heat. The energy on both sides is the same. And you should know the activation energy goes from where you start to the top of the hill because the reaction goes, remember, this is energy, y-axis, time is x, over the hill and down the hill to grandmother's house we go to the products. And for an endothermic reaction, where heat is on this side, the reactants have less energy than the products. Activation energy is still where you start to the top of the hill. Now, where I was going is let's do a different one. Let's do this one. For this reaction, what happens to the carbon monoxide and hydrogen concentration if you, first one, put it in an ice bath? What does an ice bath do? Remove heat. By the way, there's something missing here. And therefore, at equilibrium, there was a certain amount of heat. Now, you put it in an ice bath, you removed heat, and the equilibrium says, I hope you know equilibrium can talk. If you're a chemist, you can hear it. Not really. But anyways, it says, oh no, I have less heat than I need. I need more heat. How can you make heat? Carbon dioxide, hydrogen react to go this way to make more heat. Now, when things react, they're consumed and you have less of. So what happens to the concentration of hydrogen? There's less. Now, since it's going this way to make more heat, you're also going to make more CO, carbon monoxide, and water. And what happens to the carbon monoxide? Well, you're making more of it, so it increases. Next one, what happens if you put the reaction in boiling water? And here, boiling water adds heat. At equilibrium, there was a certain amount of heat. And now, after I clean up my mess, and now what you did was you increased the heat. Now the equilibrium says, oh no, I've got too much heat. I've got to get rid of this. How can it get rid of the heat? Heat can react with water and carbon monoxide, to go this way. By doing that, the heat is consumed, meaning there's less, which also means there's less water, less carbon monoxide, which means the carbon monoxide decreases. And since it's going in this direction, you make more carbon monoxide, more hydrogen, which is why the hydrogen increases. When you make more of something, the amount you have increases. And finally, the last one, what happens when I get the eraser moving? Ah, don't worry, I'll waste another half hour doing this. No, not really. What happens when you add more carbon dioxide? Well, at equilibrium, there's a certain amount of CO2. Now you've added more, and there's more than it should have. And it says, oh no, I have too much CO. I've got to get rid of some of it. How does it get rid of it? This reacts with this. When you react something, it's consumed, you have less of it, and therefore it makes more heat, more water, more CO. If you're going to make more CO, its concentration increases. If you're reacting the carbon dioxide with hydrogen to go this way to get rid of the excess CO2, there's going to be less hydrogen because it's consumed. And that's why that decreases. Next thing I taught you, which we went through and you learned quite well, is evident on test 4 scores. What's an acid? A bronzed-laurie acid. If I just ask what's an acid, that means bronzed-laurie. That's a compound that can donate a proton donor. What's a base? Something that accepts a proton, and that's a proton acceptor. You should know HCl, H2SO4, HNO3, hydrochloric acid, sulfuric acid, nitric acid are acids. Sodium hydroxide, potassium hydroxide, and ammonia are bases. In water, water is an amazing compound, and it can react with itself to dissociate, and it makes the hydronium ion concentration and hydroxide. And Kw, water ionization constant, no, it's not named after me, I wish it was, is the hydronium times the hydroxide concentration equals 1.0 times 10 to the minus 14. Now, when you have an acidic solution, that means the hydronium ion concentration is greater than hydroxide. When you have a basic solution, the hydroxide is greater than the hydronium. And for a neutral solution, the hydronium ion concentration is equal to the hydroxide ion concentration. Talked about probably one of the most important concepts I'll teach you this semester, and that's pH. And pH is defined as minus the log of the hydronium ion concentration. Shh, don't tell anybody I'm being nice, okay? Shh, be quiet. My gift to you this semester Once again, do you see pH on the screen? Thumbs up, people. Thank you. My gift to you is if the hydronium ion concentration is 1.0 times 10 to the minus X, and you put it in here, pH will be equal to X. Now, this is something I didn't ask you. I didn't give you an important information, but it's one of the few things I'm asking you to learn this semester, memorize, is this right here. Oh, that's an awful arrow. I can do better. Maybe. I did. pH goes from 0 to 14. At pH 7, halfway between, this is neutral. Anything below 7 is acidic. Anything above 7 is a basic. When you add an acid, the pH numerical value drops. When you add a base, the pH numerical value increases. The more you add base, the closer to 14 it gets. The more acid, the closer to 0. Your stomach has fluids, they call them stomach acids, which is about pH 2 or 1, depending on who you see, what chart you look at. And it's acidic because there's an acid in your stomach, hydrochloric acid. This is probably one of the most important things I'll teach you. Your blood has a pH about 7 to keep you alive. Now, I taught you about buffer solutions. A buffer solution is a solution that resists major changes in pH when small amounts of acid, like a dilute amount of acid or base, are added to that. And what it really means is if you add acid, small amount of acid or base to buffer, the pH stays the same. And finally, I talked about titrations, which are done a lot in the United States and the world. And these are used when you do a titration to, one, find out the molarity of an unknown solution of acid or base. And also, they're used to find out certain specifications, like you did in the lab for vitamin C ascorbic acid, how much was in the pill. And at neutralization, when the indicator changes color, like in the lab you did, moles of acid equals moles of base. At that point, you know milliliters of acid times molarity of acid equal milliliters of base times molarity of base. And generally, you'll be asked to either find this or this, and the other three things you'll be given. And you saw that on test 4, and that's an important skill you should have. Guess what? I've done my job. You now know that my world of chemistry is your world of chemistry, and you know a lot about it now. And with that, I'm done. Actually, today, normally, if this had been summer, today, Thursday, you would come to class and we'd have our final. But instead of being real lazy, I decided I could hold a lecture to help you out in the last day, which I did. But I'm going to let you out early because I'm done unless anybody has any questions. And with that, I'm going to do the final time this semester. It's been a fun semester. You people have been great. I really appreciate it. And do good on the final. And with that, I'm going to say goodbye. Gehen gesund, be healthy, and a big gehen gesund, be healthy the rest of the semester, the rest of the year. Remember, wear a mask and be safe out there. It's dangerous.